thinking about is, do populations always evolve? When do they evolve? What is evolution? How do we show evolution when we are graphing the distribution of some trait? If we tie evolution to the distribution of a trait, what is... What was your question? Well, what's evolution? If we're thinking about it in terms of the changing distribution of some trait, and this is our before, what would this have to look like after for us to say that evolution happened? Different! Because all evolution is a change in distribution of traits. So if this graph has changed, then evolution has happened. The population has changed its distribution of some trait. So if you look at your very first distribution and your very last distribution, are they identical? They might be for one group. It's possible. If your distributions at the beginning and the end for the and the only trait that we're measuring here is what? What trait were we measuring? Color. Yeah, color. That's the only trait we can observe about the Skittles. We don't know if they're fast Skittles or slow Skittles, or if they're smart Skittles or long-eared Skittles. We don't know any of that. We just know what color they are. So these are your partial notes. You do need to have your iPad out and be taking notes. So if the distribution has changed, then evolution has occurred. So on your sheet, if your distribution is not the same as it was in the beginning, your population has evolved. Now, for my random predators, well, let's talk first. Let's refresh. We said that a population evolves, or a population doesn't evolve if we don't have any big mutations, we don't have individuals coming and going, the population's really big, all mating's random, and there's no selection. That's when we said populations, and you already saw this, you don't need to recopy it. That's when we said they don't evolve. So, if we do have major mutations happening, or we have individuals entering and leaving the population, or the population is really small, or mating is not random and predation is not random, and there is some kind of selection, then we can expect that the population will start to evolve. So in the case of Skittle Island, let's talk to the random people first, and that's you guys, and we had some randoms back here. In the case of random predators, how many of you had a color go extinct? Okay, so in the case of the random predators, all of you had at least one color of Skittles go extinct. And I'll show you the results from one that I ran up here, because I love eating Skittles. I started off with this. I closed my eyes. I randomly ate some Skittles, which was hard for me to do. And I ended up with this. What color went extinct in my first round? Red. Barring some kind of major mutation, will I ever have a red Skittle on this island? No. Unless one of them mutates and I get a randomly produced mutated red Skittle. There are no more red Skittles on this island. They are extinct. Now, were there ever green Skittles on this island? No. My founding population had no green Skittles. Barring mutation, will I ever have green Skittles on this island? No. I'm limited by the amount of genetic diversity that was present in the start. But thinking about the fact that red went extinct, was it because red was easier to see with your eyes closed? Was it because red was giving off a heat signature that you could see? No. It was just random dumb luck that I grabbed red. I could have grabbed all the purple. Maybe red would have survived. It was random dumb luck. So the concept that I want to talk with you about is this idea of genetic drift. Because genetic drift is all about random chance. In small populations, random chance plays a big role in changing distributions. The individual with the best traits could fall off a cliff, be struck by lightning, or be crushed by a falling tree. And none of those would be the fault of their genes. Not a one.